All right, now I want to talk about how to find the matrix of various geometric transformations using the result from the previous video that we just have to follow what happens to the standard basis vectors. So let me start with an example. We're looking at 2D rotations of the plane. Let me start with a specific example. The transformation from the plane to itself that rotates points 90 degrees counterclockwise around the origin. So, all right, so if I wanted to draw what that looks like, I guess I could draw some axes here. And if I just took kind of a random vector, x, like that. So I'm rotating a point. I guess I'm thinking about rotating all the points on the vector, or the tip of the vector if you want. And then I rotate it 90 degrees, it'll be over here, 90 degrees counterclockwise, right? It'll be the same length. And that will be t of x. And this is a right angle between those two. Okay, so that's what I mean by this transformation. And it may not be obvious completely that it's linear transformation, that it should be given by a matrix, but it is. If you think about the 3 blue 1 brown video that talked about linear transformations, you know, they transform lines, lines remain lines and they remain equally spaced. You can see here that parallel lines are still parallel and still lines and are equally spaced. If you just rotate the plane, that doesn't change. If you have 2 parallel lines and you rotate them 90 degrees, they're still parallel and the same distance apart. So, so it is a linear transformation. And how do we find the matrix of it, right? So how do we find, or even the formula for how would, you know, what the transformation does? Here's the idea. We want to use the fact, this fact from the last video, that the matrix of T is just the matrix whose columns are what happens when you apply T to E1, remember, which is like the 1, 0 vector. And then the second column is what happens when you apply T to E2, which is the 0, 1 vector. Right, so that's the matrix we're looking for. And so all we got to do really is actually figure out what happens to 1, 0, and 0, 1. And that's not too bad, right? Like if I draw some axes again and think about the 1, 0 vector, when you rotate it, like let's say that's the 1, 0 vector right there. When you rotate it 90 degrees, it clearly goes up here, same length, and it actually, so this is T of 1, 0, and it's pretty clearly just the vector 0, 1, right? And, you know, this was E1 right here. And then if we do the same thing with E2, if we rotate E2, that is this vector right here is E2, the vector 0, 1. And if we rotate it, it goes over here. And that's the vector, so the T of E2, or T of, I'll just write it as 0, 1, is the vector negative 1, 0, right? Because it's kind of the opposite of E1. It's negative 1 to the left. No y component. So, all right. And so basically, what I'm trying to say is that we can just plug these in here and plug this in here, and we get our matrix. So the matrix of T, so the matrix of this rotation, of the 90 degrees rotation, is, let's see, the first column is 0, 1, right? Because of that right there. And the second column is right there, minus 1, 0. And that's it. That's the matrix. And so that's pretty easy. I will say that it's worth mentioning that you can also get just the full up formula, right? So then the formula, which you might be able to sort of get just by geometric, from geometric analysis, is that if I want to actually know what this does to a general vector, right, we can multiply by this. And remember, there's different ways to multiply matrices. You can think of this as the scalar on this column, and this is the scalar on this column, and add them together. Or you can think of dotting this with this to get the first entry, and then dot this with this to get the second entry. But either way, I think we end up with minus x2, x1. And that's the formula. So x1, x2 goes to minus x2, x1, which I think if you look at the picture makes some sense, right? Like if I think about this being x1 and that being x2, then you kind of have the same triangle up here. And that's x1. And this is actually negative x2 because it goes in the opposite. It goes to the left instead of the right. So it goes in the negative direction instead of the positive direction. And then just from, so you could have sort of eyeballed this too and sort of seen that this is the formula that you get. But yeah, so that's kind of cool, right? That we just can actually use, we don't have to sort of figure out the whole formula. And especially for more complicated situations, it will be much harder to do that. We just have to see what happens to, in each of the sort of these cases, right? What happens to E1 and what happens to E2. As an exercise for yourself, I would pause the video and see what's the matrix for rotation by 180, by pi radians or by 180 degrees. I guess it doesn't matter if it's clockwise or counterclockwise at that point. So I would pause and try to figure that out. Okay, so then I basically just want to say, well, what about the general rotation? Can we do the same kind of analysis by theta degrees or radians counterclockwise around the origin? So, okay, well, let's draw what that will look like. And remember, all we have to do is really know what happens to the 1, 0 vector and the 0, 1 vector, right? So let me try to draw this kind of nicely. I can draw straight lines. Hold on. Okay. So, all right, let me draw kind of big the E1 vector. What color did I use? Let's say color coordinated. Okay, so that's E1. Maybe I'll make it kind of big. So that's the 1, 0 vector. And then we want to rotate through theta degrees. And so if we rotate it by some angle, it'll be like that now, right? So let's say that's theta. That's our theta. And so this vector then is t of 0, 1. No, sorry, 1, 0. And we really want to know the coordinates of the tip of this vector, right? We would like to know like what this point is right there, because that we want, you know, what does this equal? And the way to think about this, I think, is just to draw, if you just draw this kind of nicely, right? We have this vector like that. Oh, wow, it turned into an arrow. Didn't even know Notability did that. Okay, so, but then we think, okay, well that's, and if we draw sort of the horizontal piece again, no, it doesn't want to make a straight line. Okay, I don't have to actually draw a straight line, but I'm, oh my God. Okay, you know what? That was dumb. Guys, I'm just gonna draw approximations of straight lines. I don't have to be that crazy. So this is theta. And we would like to know the coordinates, you know, we have the origin down here. And we'd like to know the coordinates at that point. But here's the thing. How long is this vector? It's length 1, right? Because rotating the E1 vector 1, 0, that's length 1. It doesn't change the length. Okay, so, and then the question is, well, what are these X and Y coordinates right here? Well, it's kind of clear, right? Think about it for a second. What is this length right here? And what is this length right here? All we know is that the hypotenuse is 1 and that the angle is theta. Doesn't really look like a theta. Let me try to draw that again. So ask yourself, what are those legs equal when the hypotenuse is 1 and the angle there's theta? And you know the answer, right? This is cosine of theta, and this is sine of theta. It's exactly the kind of the definitions of sine and cosine. So in fact, this right here is, take away the question mark, it's actually is, didn't erase the question mark, okay. It actually is cosine theta comma sine theta. Nice. Now, what about, so that's actually going to be the first column of our matrix, right? Now, what if we take, all right, how fancy do I want to be? Can I take this and actually copy it, paste, and rotate? Can I do that? Kind of. All right, let me erase some of this stuff. And oh, I wanted these to be a different color, right? I think I can do that also. Oops. They were orange before. Oh, I made the whole axis orange. Let me not make the whole axis orange. All right, so this is the exact same picture, just rotated. This is the vector 0, 1 now, and this is t of 0, 1. But if I just rotated the whole thing, you know, it's sort of the same as taking this, this triangle over here and rotating it 90 degrees also, right? Oops, I don't want to delete those. Getting too fancy with my notability, and it's probably just causing problems. But okay, so if we have this picture, well, this quantity is still cosine theta. Ooh, that was exciting. And this quantity is still sine theta. Oh my God. Okay. Except I claim this has a negative sign in front of it now because it's going to the left. It's going in the negative x direction, right? And so look, so it's the exact same picture, just turn 90 degrees. And in fact, that means that this over here, t of 0, 1, is in fact, the x coordinate is minus sine theta, and the y coordinate is cosine theta. Okay, and so the matrix of this general rotation, so the matrix for rotation by theta is, well, we just take what we got from here, and that's the first column, and then this is the second column over here. So let me just copy that down. Cosine theta, sine theta, minus sine theta, cosine theta. And that is our matrix of rotation. Very exciting. Okay, and so another thing you should check as an exercise for you is to check that this gives what we expect for theta, for theta equals 90 degrees and 180 degrees, which are matrices, rotation matrices you already found, right? So that should work. But it's kind of neat. Now we can actually write down the general rotation. You could also multiply this matrix by x1, x2 to get the sort of general formula, but it's not that illuminating. It's just the matrix is what you want to try to remember. And it's got that nice pattern, the cosine, sine, minus sine, cosine. So, all right, that's general rotations. We'll do some other categories of geometric transformations in future videos. All right, I'll stop there.